Until now, we discussed exponential function y is equal to e raised to power x. Here, the base was e. Now, we want to extend such functions for any base. So we are talking about y is equal to e raised y is equal to a raised to power x. We are talking about such functions, which are also called exponential function, but usually we call it general exponential function. We start with some mathematical equation. We can write a is equal to natural log of a. E and natural log will be cancelled out, so we get a over here. We can also express this as e raised to power natural log of a. E raised to power natural log of a, if I take a derivative, if I take a power of x, and also a raised to power of x, both side, and the right hand side, if I can write this as e raised to power natural log of a raised to power x. So we have natural log of a raised to power x is equal to e raised to power x natural log of a. So these are equal to each other. This is very important result. Sometime in future, we can write a raised to power x as e raised to power x natural log of a. So the definition is we can write a raised to power x. Since the left hand side, you can see that it is a raised to power x. A raised to power x can be written as e raised to power x natural log of a. For a should be greater than 0. This is also an exponential function, but with base a. Exponential function with base a. When a becomes, for example, when a becomes e, then we have e raised to power x is equal to ex natural log of e. Natural log of e is 1, so e raised to power x are equal with each other. Let us just see the exponential function laws. If we have two functions, a raised to power x1, and we take a product of these two functions, a raised to power x2, that will be equal to e raised to power x1 natural log of a multiplied with e raised to power x2 natural log of a. According to the laws for exponential function with base e, we can add the powers. E raised to power x1 natural log of a plus x2 natural log of a. Then it can be written as e raised to power x1 plus x2, taking natural log of a as common over here. Then we can see that the definition over here, the definition says that if there is an x over here, then we have x over here. If we have, for example, y natural log of a, then we have a raised to power y. If we have, for example, z natural log of a, then we have a raised to power z, something like this. If we have ex, the power contains x1 plus x2, then we can write by definition a, the power of a will be x1 plus x2. So we write it as a raised to power x1 plus x2. So this is the exponent of two functions multiplied together. Okay, from here we can simply write, for example, x1 becomes n and x2 becomes minus 1. So we have a n minus 1. Okay, there is one general version of this law. Suppose we have y is equal to x raised to power n. For x greater than 0, we can write it as x raised to power n e raised to power n natural log of x. How can we write this function? Uh, Simply, you can write the right hand side as e raised to power natural log of x raised to power n. So e and natural log cancel out, we get x raised to power n. So this is the very important result where we have natural log of x and exponential which are inverses to each other. When they are inverses, we can get many other definitions coming along with it. Okay, what will be the derivative of such function? Now this is our second question. For x greater than 0, the derivative of such function is quite simple, xn. This is nxn minus 1. So this is the formula. Okay. If x is, for example, less than 0, then you have to adjust your derivative accordingly. Let me just prove it for you. We already proved this formula in the chapter where we discussed differentiation. Let me just prove here differently. Proof. D by dx xn will be equal to d by dx e raised to power n natural log of x. When we differentiate right hand side, we can see that we have to apply the chain rule. The derivative of exponential function, is the same. But when we have some power other than x, then we have to apply the chain rule. And the chain rule becomes e n natural log of x d by dx n natural log of x. The right hand side becomes e natural log of x raised to power n, and n is just a constant, and we need to take the derivative of natural log of x. E and natural log cancel out, so we have x raised to power n, and the derivative of natural log of x is x. So we have n xn minus 1. So it is only true when x is greater than 0. If x is, for example, less than 0, suppose x is less than 0. When x is less than 0 and y is equal to x raised to power n, and when we take the derivative y dash x, then y dash and x minus 1 will exist only when we have natural log of y mod is equal to natural log of x mod n natural log of x mod, something like this. So if it is written like this, so we actually apply the implicit differentiation. So we have 1 over y dash, and then on the right hand side we have n over x. And from here, y dash is equal to ny over x. So we are proving that the derivative of xn when x is less than 0, we need to find the derivative of such function. Y was xn over x, and y dash is n xn minus 1. Y dash n xn minus 1. Okay, so this is just a derivative on the left hand side. We integrate that and we get the answer at the end. Okay, the next we have one example over here. Example. We need to differentiate y is equal to x raised to power x. That is very interesting. And x is greater than 0. By definition of a raised to power, definition of a raised to power x. What was that definition over here? The definition was this equation. We just copy that and place it over here just to remind that this was the definition. So when we replace this a with x, for example, x raised to power x, then we have e raised to power natural log of x. This a is becomes x, and this x is written over here, or maybe this a is natural log of x. So we can write, I just put it this definition at the bottom. Take a derivative dy by dx, d by dx, and e raised to power x natural log of x. Differentiate right hand side by using the chain rule. E raised to power x natural log of x, d by dx, x natural log of x, e raised to power x natural log of x, and we have natural log of x plus x over x. So by solving this, e raised to power natural log of x raised to power x, natural log of x plus 1. The first term becomes x raised to power x natural log of x plus 1, and remember that x is greater than 0. So this will be the derivative of when we have x raised to power x. That is a very different derivative over here. Okay, so this was all about the exponential function with base a, with base x, and the power is also variable over here. Thank you for watching.